So last time I spent all my time talking about how the technology works. So I'm not going to do that today. If you want to hunt me down in off hours or out on the balcony, I can explain it to anyone later. I'm just going to tell you what our group did, what our group does, and then give some background on why it's necessary. So this is a molecular modeling workshop. Every other field of technology and science benefits a great deal from modeling and design. It's unthinkable that someone would do trial and error on an antenna design these days, right? Most wind tunnels have been decommissioned. You just check supersonic planes once in a while, on the shared, wind tunnel. But most of the work is done in, FEM or whatever. Even neural nets speed up your differential equations by a great amount by learning them. And everything we talk about here is actually known to humans. It's governed by laws of quantum mechanics, specifically computational quantum mechanics for molecular interactions. But actually, none of the modeling tools that we're used to in every other field have actually been useful in molecular modeling. Let's take a look at a state of the art. So you mentioned DFT, unfortunately, in the same camp. So if you're just to dissolve sugar in coffee, right? We're not even talking about salt, but sugar, right? Which is, a polar but not ionic molecule. The error on various types of simulations, will be approximately 4 to 5 kilocalories per mole. Essentially, the error will be as much as the value itself, right? And it's a random number. DFT, someone mentioned DFT, is actually complete. It's not tractable. If you ever actually try to dissolve something with DFT, you'll know why. There's duct tape here, duct tape here, duct tape here, duct tape here. Meanwhile, you know the answer. So, for example, the prediction of the pK of water by DFT has drifted over time as the experiments have drifted over time. Kind of amazing, right? Okay. But I mean, there's a lot of, and anyway, so by the way, in the history of science, I'm going to ask you a question. How many ionic solvations have been actually experimentally determined? 10, 100, 2? It's 5 or 6. It's actually a difficult thing to do, right? Ions don't exist in isolation. So ionic solvation is far worse, right? So this is actually very important for batteries or just, putting salt in your food. And the error of that is actually maybe a third or half the temperature of the sun. And again, it's fairly random, and most of the things that people look at have been produced by knowing the answer ahead of time. Lithium ion, of course, has been measured exquisitely in various things. This is old school physics. We'll see a slide in a second that'll show you. This is basically models that have existed since 1960. OpenMM is circa 1966, designed originally by my coworker, Michael Levitt. I'll show you in a second why essentially everything that's been produced up to now for things of interest is essentially a random number. I'll tell you exactly why that's so in a couple of slides. This is actually, I'm going to poo-poo on this a little bit, but I want to say AlphaFold and people who did this before them, it's a brilliant exercise in evolutionary inference. It's fantastic, right? And AlphaFold, I know the people who did it before, but what AlphaFold tells you, let's just think about it, is how 21 molecules, maybe plus water, 22 molecules, like to be together in a system which is evolutionary put together incredibly loosely. Because if proteins were tight, I would not be able to talk or move my hand or anything. I'll be a rock. So it's a very special set of circumstances, somewhat limited. It definitely doesn't extend to anything that you might want to do later strongly, like drug design, right? So zero correlation to energy and some other things. Worse than just trying a lock and key mechanism for drug design. And the fonts are fine. So because we're a company, you can also prove this by looking at market caps of various things. So people like ANSYS and Altair are selling Bernoulli's equations, which obviously they didn't invent, but they were invented in the 19th century, and they're in almost every engineering toolbox, a piece of them, and their market cap's quite high. There's other companies doing that. That's that's incompressible liquid modeling. A company like Schrodinger that's supposed to do everything atomic, atomistic, is worth 1.5 billion in sinking, and our thesis is because they're not actually predictive, right? And so if you actually go ask around, that's the case. Quantum computing, we can discuss that later, but you know, it's a breakthrough away, or at least one. So, you know, someone will do it, and I'll say great, but right now breakthroughs are, you know, not there. So to actually predictably model atomistic systems is known to be a hard problem. Okay, so some famous people, you know, opined in 2017 that it's like 50 to 70 years away. You know, modeling of atomic systems probably started with the Monte Carlo method, right, at the Manhattan Project. Right, 1968, people started to do things like OpenMM, and our group has done it. So just when I have a little time, I just want to impress upon you why it's incredibly exquisitely difficult. So the way molecular machines work in nature, sorry, yes, okay, 1 minute, yeah, is by, take a look at specific mechanism. This is an enzyme or a drug. You're looking at an answer that's minus 2 kilocalories per mole. That's your final answer. These are some of the energies involved in this system, okay? So when you talk about DFT, each component is plus or minus 3 kilocalories per mole, depending on how you do it. You can see this is an exquisitely difficult thing to do, right? And so the final shot, I guess, is that if you get more and more accurate, eventually you bypass the threshold of random numbers and you start seeing things, right? So like when you get more focused at the optometrist, if you don't have enough focus, you don't have less information, you have no information. And so as you make these things more and more precise and accurate, eventually you start getting correlation to experiment, and that is exactly what our group did. And I think that's basically it. And if you're interested in knowing more or how or what, you can talk to me later. We are fundraising, of course, for our seed round. We've raised a pre-seed, so that's something I'm supposed to say. If anyone's interested in that, you can talk to me later. We should be closing the round in about a month and a half. Any questions?
Thank you.
That's it.
Okay.
Yes, sir.
We'll start over here.
Yeah.
So what are the sizes and timescales that you can handle in your simulation?
So you sound like you really know what you're talking about. So they're, it's about a polarizable force field speed, like an amoeba, that type of thing. Yeah, yeah.
How broad a scope of systems can you analyze? Just proteins, DNA, whatever?
I mean, so the information that these models use to benchmark, to train themselves comes from quantum mechanics, small pieces of quantum mechanics. So I think the only trouble we would have at this point is maybe extended conjugated aromatics, because they are just big things in themselves. Yeah. Yeah.
Emanuele, just shout it out.
That's it. Yeah.
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 How far are you from simulating chemical reactions?
So, okay, great question, right? So that we're mostly interested in biology. We're not interested in reactions at the moment, because the only reactions we really see are pronation to pronation. Also, reactions, just if you're in an enzyme, if you're put in place, in the proper place in a strain, it'll just happen. Also, the pathways of reactions are not actually, the actual pathways are not well modeled by quantum mechanics, like the intermediate states, So for all these reasons, it's probably easier, which we are playing with, to just, click it on and off. It's not, and the time scales, we kind of know all the reactions that happen, right? It's much more important and intricate to set up the enzyme with the strain and proper electrostatic, mechanism to actually make the reaction possible, also, it's kind of a cheat, right? We also use DFT we use, couple cluster to get intermediate states, and then we can jump them on them. The actual making of a reaction is not something I would recommend doing right now. Yeah, that's right. Yeah. Yeah.
Okay, well, thank you, Boris.
Yeah.
That was great.
Thank you.